Hello everyone, today let's take a look at quantipus number 67, another integer partitions question. So let p sub k of n be the number of ways to split n identical balls into k unlabeled boxes where boxes may be empty. So given that p sub 4 of 100 is this number and p sub 5 of 95 is this number, what is p sub 5 of 100? And this question is just to demonstrate probably the only interesting property of integer partitions, and it's that there's some type of recurrence relation. So let's look at what we're given here. We know p sub 4 of 100 is 7,540, and that just means the number of ways to break the number 100 into 4 parts is going to be this. So for instance, I could have 100, 0, 0, 0, or I could have 99, 1, 0, 0, and many more, and we know that there's going to be 7,540 of them. And the second term tells us that there's going to be 6,213 ways to partition 95 into 5 parts. So again, for instance, I could have 95, 0, 0, 0, 0, or I could have any of these, and there would be 6,213 in total. So now it's asking us, what is the number of ways to split 100 into 5? So now we ask ourselves, why did they give us these numbers here? Well, there must be some type of relation, so let's figure out what it is. First question I would have is, why the number 95? We'll notice that if we started off with our 5 boxes down here and we just gave 1 to every single one of our boxes like this, and then we took our 95 objects and distributed them to these boxes, well, the number of ways to do that would just be p sub 5 of 95, which we know. And notice that once we do that, we basically have the number of ways to partition 100 objects into 5 boxes, given that no box can be empty. Right, this is basically what we did in quantipus number 82. So let me just restate that. If we do it this way, where first we distribute 1 item to each box, and then we distribute 95 items to these 5 boxes after that, well then that's just going to be the number of ways to distribute 100 items into 5 boxes, given that no box can be empty. And what are we trying to find? Well, we're just trying to find p sub 5 of 100, which is the number of ways to distribute 100 items into 5 boxes unrestricted. So if these are the number of ways where no box is empty, well then we need to add back on the number of ways where a box could be empty. So how do I calculate that? Well, let's formulate the problem over here. Let's say I have my 5 boxes and I want one of them to be empty. So there's going to be 0 items in one box. Now I have 100 items left to distribute to the 4 boxes remaining. And would you look at that? The number of ways to do that is exactly what the other term was in our question, p sub 4 of 100. So again, just to restate, p sub 4 of 100 is going to give us the number of ways to distribute 100 items into 5 boxes, given that at least one box is empty. And this term over here gave us the number of ways to distribute 100 items, given that no box is empty. So when we add these two together, we're just going to get the total number of ways to distribute 100 items into 5 boxes. So if we come back up here, the answer to our question, p sub 5 of 100 is going to be equal to the two terms added together that we were given, p sub 4 of 100 plus p sub 5 of 95. So when we just plug in the values we were given, right, 7540 and 6213, we're just going to get 13753. So this is the cool relation behind integer partitions, right? And can we generalize it? It turns out we can, and the formula for that, I'll just write it down here. So this is going to be the formula that describes this relation. It's saying if we're distributing n identical items into k identical boxes, then we have this relation where it's equal to the number of ways to distribute these n items into k minus 1 identical boxes, plus the number of ways to distribute n minus k objects into k identical boxes. And the reason this works is because we're just distributing this into disjoint sets, right? This term right here is going to be the number of ways to distribute the items, given that no box can be empty. And then this term here was going to be the number of ways to distribute the items such that a box must be empty. One more thing, this is only going to be true when n is greater than or equal to k, and that's pretty clear because when we do n minus k in here, if n is less than k, well then we're going to get a negative number, and that doesn't even make any sense, right? So what would the relation be when n is less than k? Well, it actually turns out that p sub k of n is just going to be equal to p sub k minus 1 of n when n is less than k. And it's pretty easy to see why this relation over here is true when you just work out some basic examples, which we will do in the next question, so we'll go into this more then.